Okay, so the main reason Elena asked me to introduce the speaker is so that I can show off that I can read Mandarin. So, as you can see, the talk is by Shi Jin. And the talk is... But you are commuted.
I was checking.
The talk is on RBM for IPS and CBO for HDMLP. Please.
All right, thanks. First, I'd like to thank Ari for putting together this interesting program, for inviting me here. It's really always great to be Newton. So because I'm in Newton, I decided when I got an invitation, I said I have to do something that's related to Newton's equation. So that's what I'm going to talk about. So I have two parts here. The first one is basically how to solve Newton's equation. Second part, how to use the Newton equation for the new things like machine learning, all this stuff. So these are all interacting particle based. All right, so here's the Newton's equation. Basically, you have m particles, position particles xi, ice particle velocity vi. So the first line is dot is time derivative. First line is just definition. Second line is f equals ma. All right, assume m is 1. So velocity time derivative is a. The right hand side is just forcing term. The two parts, external force and interacting force between particles. Here, every particle has to interact with all the other particles. Right? So this is all the n summation. If you take some limit, like over-damped limit, you arrive also at this first order system. Well, again, this is a particle xi. This is external potential comes from some force, potential gradient, metric gradient potential. Then you have this interacting potential. You can also add a noise, Brownian motions. So this kind of equation we're going to talk about, we'll try to solve numerically. Of course, talking about applications, basically Newton's equation is not just applied to stars and molecules. Of course, it works there, physics, chemistry, molecular dynamics, for example. You solve these kind of equations, electrostatics, astrophysics, models stars, galaxies. And also in the last decade or so, there's emerging applications of biology called collective behavior of agent-based model, like flocking, swarming, chemotaxis, and so on. And even in social science, we do things like mean field games, consider particle models for mean field games, for wealth distributions, opinion dynamics, and so on. One could also formulate, for example, clustering problem in data science as a particle system. Not to mention that this is a numerical program. Particle method is an important class of numerical scheme to solve, for example, kinetic equations, mean field equations, and so on. So essentially, if you are a computational scientist, it's a big probability that you will solve one of these equations in your lifetime. And of course, here the keyword is that m. So m can be very, very large. Here I took slides from Pierre Emmanuel Jaban. So here I just show you that in all these different applications, n can be easily 10 to the 20s, for example, 10 to 10, whatever. Right. So that's the main issue here. It's not we cannot know how to solve ODEs, but the question is we cannot afford when n is very large. But on the other hand, sometimes when n is very large, you can take a mean field limit. So if you define so-called empirical measure, if you put the discrete Dirac mass for particle xi, and you take average, that's called empirical measure, and you take n to infinite, under certain assumptions on these potentials v and k, this marginal distribution, or either the marginal distribution of n particle system or the empirical measure can be proved converge to this Fock-Planck equation, where this is come from external force, this interacting potential, and you get this convolution between k, this interacting potential, and density distribution. While the Brownian motion, of course, give rise to this diffusion term. So that's the so-called mean field limit. And here, of course, the main problem is that if you solve this ODE, for each time step, it's all the n squared operation. Because you have this summation here, it's all the n, right? All the summations are all the n summation for each particle, but you have n particle. So the cost is all the n squared. Or if you have, it's not binary, if you have more particles interact at the same time, it's even n to some bigger power. So of course, the lot of important algorithms were introduced to handle this difficulty, for example, fast multiple methods. But it works quite powerful when you have short-range interaction. For long-range interaction, it becomes very complicated. And today I'm going to show you a new method, which is embarrassingly simple. But it does this work and reduce from order n squared to order n per time step. And it works for general interacting potentials, not just for short range, but also for long range. And when I say embarrassingly simple, I really mean it. So it's joint work with Lei Li, who is a new colleague at SJTU. Got his PhD from Wisconsin and was posted at Duke. Jiao Liu is a faculty at Duke. So this algorithm, just two-line algorithm, all right, very simple. So at every time step, we first discrete time pickup time step. So first, we have these m particles from particle 1 to particle n. We do a random reshuffling of these m indices. And then we divide these m particles into little n groups. Little n group, each group has p particles. All right, and this p is much less than capital N. For example, you can even take p2 equals 2. Basically, you divide, you just randomly regroup all these particles, for example, into a small group. Each group has a p particle, just 2 particles. All right. Now what you do is just let particle only interact within its own group in your own batches. Right? You divide them into small group, and they only interact within the group. They don't interact with the particle in other group at each time step. Okay, so that's the algorithm. Very simple. If you write a code, just few lines, it took half an hour. So you select time step. So suppose you have done m time steps. Then first you do a random permutation. You divide this from 1 to p time letter is capital M, little m batches. Each batch has a p component. Then all you need to do is replace this order n summation into order p summation. So you only add this interaction within your own group. Okay, you forgot about other particles. So that's the algorithm. So this algorithm we call with replacement. The cost is clearly order n because this random shuffling algorithm, that part is already in the 60s, people already introduced method which you can do that random permutation order n. For example, if you do MATLAB, you just call this subroutine, that's it, random permutation. That's order n. The summation clearly is order n, maybe the summation is order 1, right? Because you only have little p can be 2. You only interact with one more particle, clearly that's order n. You have n particles, so the ODE part per time step is order n. So overall, each time step is order n. Okay. You can do it differently. You can do it what we call the random batch method with replacement. So what you do is you have m particles. You draw p particles randomly, let them interact, then put it back into a basket. Then draw another p particle, let them interact, put it back. After you've done little n time, you finish one time step. Then you repeat. That's what we call a with replacement. So you can do these two different versions. All right, so clearly the computational cost has been reduced by n. The question is, how about your time step? Does it take much longer time to finish this process? Clearly, if you only interact within a small group, you're not solving the original equation. You're not solving the right equation. All right. Intuitively, probably you need n times more to finish this process. But we're going to prove actually. You can choose the time step. We can prove for under some assumption on this potential. Time step is independent of capital N, which means it does not take n times longer to finish this process. All right. It sounds a little bit too good to be true, but this is a basic law of large numbers. Okay, that's the magic of a probability. Another bonus is that if you do a first order system, if you do Coulomb interaction, and if you choose, if you do p equals 2, which means you have two groups within 2 particles in each group, if particle interact with one more particle by Coulomb interaction, I mean this ODE, you can solve it analytically. When you have Coulomb interaction, it could become singular if xi is too close to xj. It's singular, then ODE is very stiff, your time step has to be very small. However, if p equals 2, and if you only do Coulomb with one more particle, you can solve that analytically, so there's no stiffness. So that's actual bonus for Coulomb. All right, of course you ask how did you have this crazy idea? And actually there's some relevant ideas in our community. We know nowadays the puzzling word about scientific computing is machine learning. In machine learning or deep neural network, basically what you do is try to find a minimum of some loss functions, or global minimum loss function. And this loss function usually is a very high dimension. The dimension depends on the number of training data, and lots of loss functions. So of course the method of choice for minimization is the gradient descent method. However, here you have to take gradient of a very high dimension and lots of functions, summation of lots of functions. So what people do is they use the so-called stochastic gradient descent method. So at each iteration, you just randomly pick a small number of directions. So now, small number of loss functions, you only do gradient descent along those directions, along those small number of functions. The two benefits here are, number one is of course the computational cost is reduced. Number two, basically this randomness add noise to your algorithm. And here you have to solve a non-convex optimization. Usually a deterministic algorithm, if you get stuck into local equilibrium, you get stuck there forever. But this added noise actually allows you to jump out of this local equilibrium, makes it more likely to converge to global minimum. All right. Also, if you come from Boltzmann community, you know there's a very important method called direct simulation Monte Carlo method, pioneered by Birds, where you also, in Boltzmann, of course, you do binary interactions. Physically, they are mostly binary. So numerically, what you do is that you pick up two random particles, let them do binary elastic collisions. So that's another way to solve Boltzmann equation, instead of discretizing this PDE. So these are sort of related ideas. All right, so here's a little theorem which shows to convince you that it really works. So first we'll make some assumptions, and we assume this external potential is strongly convex. All right, it means it's more convex than a harmonic oscillator. And assume, of course, the first two derivatives can grow like x to the power q for some positive integer q. While for the interacting potential, assume it's bounded, Lipschitz. L is Lipschitz constant and has bounded second derivative. And we also assume this R is bigger than 2L. Basically, with this condition, these are the basic assumptions for the original dynamic system to be a contraction map. So under the same assumption, you can prove this dynamic system without Brownian motion term. This ODE is a contraction map. Same assumption. All right, we do not assume more. And then under this condition, without Brownian motion, actually you can prove if you have two initial data, you have these two solutions. So L2 normal with time derivative is bounded by itself, time is constant, under this condition, this constant is negative. So it's a contraction. Of course, this is boring because our particle will just eventually converge to the same point. But if you add a noise, of course, you get non-trivial equilibrium or invariant measure, like Gibbs measure, Maxwellian, things like that. So that's the assumption on these potentials. And now it's just simple notation. Analytic solution is xi. Numeric solution we add tilde. All right. So this is error between the analytic solution and numeric solution. We take L2 norm because these are vectors. Take expectation with respect to permutation and take square root. It turns out this error actually is also equivalent to versus 2 distance. If you take these are random stochastic differential ODE and x and y, with ties joint distribution with marginal distribution that gives the PDF of x and y. Okay. So once you have error estimated on this, you also get the versus 2 distance between these two empirical measures of these two random variables. Right. So here's a theorem, a very simple theorem. Basically, this error. We have the error estimated for time. All right, error is bounded by essentially square root of time step. Okay, So basically what we have is a Monte Carlo in time. You know, if you have Monte Carlo method, it halves all the convergence. Here we have Monte Carlo in time. So that's why it's a square root delta t, square root times that. But what is important is this constant. Under this condition I showed you on V and K, the constant is independent of capital N. If it's contraction, it's even independent of P because you have exponential decay of solution. But the key word here is remember the constant is independent of N. Which means if I want the error to be smaller than some tolerance, all I need is pick up time step to be, square root time step bound by that small error. And there's no N here, there's no N here. So indeed, the computational cost is reduced by N, but does not take N times longer to finish this process. Okay. Well, similarly, of course, if you use Watson's two distance of these two empirical measures, the analytical empirical measure and numerical one, you also get the same error. Again, this constant is independent.
But you need the potential to be smooth.
Yeah, for the proof, but for computation, I show you it works for singular potential, including Coulomb.
Do you see possibilities of generalizing?
Not yet, not yet. Now why it works? Just some heuristic things. This proof actually is very simple. Basically, it's consistency plus stability. Well, when I say it's a contraction map, that's the stability, all right? Under this assumption on this potential is stability. You can see the consistency here. So what we did is just we replace this order N summation by order P summation. Of course, this is not zero, all right? So difference, that's the truncation error. Okay, that's all we modify this ODE, this part by that. But you can prove actually, it's a very simple proof. If this axis is independent of the permutation, the expected value of this is zero. All right, so the expected value of this order P summation is the same as the order N summation. So that's kind of consistency. So the leading order truncation error is mean zero. The next order, you combine the next order error with the stability, you get the proof. Well, of course, it's stochastic. You need a little bit of Ito calculus, but it's very simple. Just I think it's 3 or 4 pages proof. You have questions? No. You can also compute the variance. So I replace this sum by that sum randomly. The variance actually can calculate exactly, which is this. And this lambda, of course, depends on this interacting potential. But it's order 1 quantity because n term summation divided by n, all right, essentially. It's order n, order 1 term. And here you see how the group size, small group size affected the variance. Of course, it's 1 over p. P is each number of particles each group. If you increase p, of course, you reduce the variance. In particular, p is n, the variance is 0 because that's the original algorithm, no randomness. Well, you can also, well, I will say that this is clearly is an approximation to the original particle system. But if n is very large, as I mentioned, sometimes you can take a mean field limit. You get this Fock-Planck equation over here. And our method can also be viewed as a particle method to solve this Fock-Planck equation if n is large. Because under certain assumptions, well, it has to be smooth for the potential. You can prove this from this empirical measure of the particle system to the Fock-Planck equation when n goes infinity. That error is about 1 over square root of n. So that's a mean field error. All right. And of course, you cannot prove this for Coulomb, but for under certain regularity assumption of potential, you can prove this. And then basically, this numerical random batch method, you add these two errors. From here to here is square root delta tau. Square root tau from here to here is 1 over square root of n, basically. Then this can be also viewed, when n is large, can be viewed as a particle, numerical particle method, good numerical particle for this Fock-Planck equation. All right, any questions so far?
Can you reduce the variance by taking the second bit?
Well, that's a very important question. Of course, here only I showed you the expected value converges. All right, but we know this variance can be large. So we do not have an estimate for the variance, the decay of variance. However, it's important to combine this with some variance reduction method to make reduce variance. Those are certainly, we haven't considered that, but it's certainly important question to ask. Any other questions? Yes?
So you take any permutation.
Yeah,
So uniform distribution over the set.
it's uniform, yeah, it's unbiased.
Okay.
It has to be unbiased, actually.
Is there any way of thinking about it as a splitting method?
Well, that's a good question. If you, yeah, you can view this as a sort of ADI. Of course, this is not a, it has some, yeah. Actually, later with Francois Gauss, we are working on quantum random patch. I think in a few weeks, we'll finish paper to prove it also works for unbody Schrodinger when you replace this Coulomb interaction by a binary interaction. The proof was quite involved there, but that's more like ADI because you have this Laplacian in very high dimension. Each time you choose two directions, then you have this two particle interaction. That's very much like ADI. But to prove the theorem, it's very involved for quantum. For classical, the proof is quite simple. But for quantum, you need a new metric, which is not much. But yeah, certainly that's an interesting analog. Okay, well, I just list, as I mentioned, this particle system arise everywhere, and I just show you a few applications. And these are the applications where this potential does not satisfy the condition of the theorem. Okay. So the first one is so-called Dyson Brownian motion. If you, for example, if you want to find eigenvalues, a mid-matrix value, the Einstein-Uhlenbeck process, and it's n by n random matrix, so the J's eigenvalue satisfy this particle system. So this is come from external potential with a harmonic oscillator. And this interaction potential, as you can see, is very singular. It's 1 over lambda I j minus lambda k. Then you have this Brownian motion term. And this equation actually has a mean field limit, which is given here, where this h is Hilbert transform. And actually, when beta equals 1, you can find an analytic solution to this mean field limit. It's given here. Solution in time, if you take t to infinity, you get this so-called, the invariant measure is this semicircle law.
I think it might be important to remind everybody that in Erdős is not Erdős.
This is
Erdős
in Jiao is Hongzhe Jiao in Harvard. It's not ST Jiao.
Tong
It's not this combinatorics Jiao. This is younger Jiao. He used to be in
Exactly.
Georgia Tech. Now he's in Munich.
I think he was at Harvard.
Jiao is at Harvard.
Erdős.
But this is Lazy Jiao.
Laszlo
Lazy
is in
Jiao
Vienna.
is
He's in Vienna.
It's in Vienna.
Yes.
Tau is Tau.
Tau is Terry Tau.
Tau is the real Tau.
And actually, we have this. Remember, we have these two versions: with replacement, without replacement. These are the two methods, and they give similar result. This initial data, this invariant measure. These are some transient solutions. As you can see, we can follow the solid lines are analytic solutions. So as you can see, we do capture the analytic solution. Well, you see, it's you have noise because it's a random method.
So
So-
the
Yes.
analysis you showed was without replacement, right?
Yeah, we cannot prove anything for this. Yeah, we are not prove a theorem for that. We can only prove theorem for the random permutation. But the numerical they works similarly.
Can you explain what are the difference in the three graphs on each row?
T was 0, initial data.
All right.
Some intermediate solution, and this is global equilibrium, this invariant measure. You see, semicircle is half the circle. Well, this is this very classical problem in physics, electrostatics. This is a classical Thomson's problem, where you put the n electrons on a unit sphere, randomly initially, and they ask what is the equilibrium distribution and the Coulomb interaction. These electrons do Coulomb interaction among themselves. The analytic solutions actually for small n. I don't remember for n to 2 to 12. You can solve some of it analytically. But here we're talking about the case when n is very large. And the solution actually is the minimize of this energy, where this kernel is highly singular because it's Coulomb interaction. And if you take actually over-damped limit, then actually you can solve this problem by solving this interacting particle system. where this F is Coulomb interaction, and this P is projection operator onto the unit sphere. And then here you also have a Brownian motion on the sphere. Right? So you solve this particle system. As I said before, if it's Coulomb, if you take a P equals 2, and this you can do Coulomb analytically. So that's what we do. So basically, we have a splitting method. You do this Coulomb analytically for we choose P equals 2. You do Coulomb analytically. And if you after you have done this for all particles, you divide each particle by its length. Then that's a projection to the sphere, unit sphere. So it's just very simple two-step method.
How does it compare to the methods of people like Sylvia Serfati and Saf for direct computation, for fixed n rather than large but not tending?
Yeah, you can of course you can solve the look for the minimum of this energy. We didn't compare with that. And so here is you see the decay of energy. Here we have particles equals 60 and 800. That's the decay of energy, and also the global equilibrium actually is a uniform distribution. So you do see a uniform distribution in each case. Well, this is some model which is mean field model, game model by Pierre de Gong, Jianguo Liu, and Christian Linhofer. You consider basically M market agents with two attributes. You have economic configuration Xi, the wealth is Yi, so the Xi and Y are coupled by this very complicated particle system. We use this example to show you, actually it's going to be very long range. Well, Coulomb interaction is already long range, but it decays in distance. This model actually is grow in distance at this phi. That we choose actually is 1/2 y squared. If you take gradient, is y. So this interaction grow linearly in distance. And another point is that it's a multiplicative noise, right? We had a theorem for additive noise, but the algorithm also works for multiplicative noise. That's one way we use. So here again, we compare our method and the one. You would solve it in the Brutal force, and we get basically a similar result. So it works for long range, very long range, when the polynomial grow in distance. This so-called stochastic opinion dynamics for so-called consensus. It's a model proposed by Moshi and Aidan Telemore, where you consider M persons, for example, they interact with all the other persons, they pass some their political opinions, for example, the influence, and then in the end you want to see they form some consensus of opinions. So this phi is called an influence function. And of course, this is clearly a non-local operator here. What we did, actually our model, our algorithm is not only an algorithm, it's also a model, a way of modeling. Because instead of you pass your opinion to all the rest of the world, you just randomly pick up someone, you tell him about your opinion at each time. So particle xi will just talk to particle x theta randomly. And then maybe you have some Brownian motion. It's kind of binary interaction, random binary. And the result actually is pretty much similar. So if you here the function is a discontinuous function, potential. All right, you only talk to someone whose distance is 1 to you. So this is a picture you see in Aiton's paper. If you start some initial configuration, eventually forms 4 consensus. And our model actually gives this additional singular. Someone always does not go along with the mainstream opinion. Very much like almost half the people vote for Hillary, the other half vote for Donald Trump. There's always people in the US, the ballot always allow you to fill out other names. Some people even put Donald Duck or Mickey Mouse. There's some singular person. So we do have some singular behavior. It's not exactly the same, but but you never know. You can argue because it's social science. It's not a rocket science. Can argue this model is more correct than this model. I mean, they are about the same, except there's some small difference. Well, some other, I probably skip some because I want to go to the next topic. So any questions for this random batch method? Okay, if now I go to this optimization problem. Of course, it's related. So, as I mentioned, if you do machine learning, what you do is you try to find a minute. Basically, you have this set of training data, xi hat, and y corresponding value is yi hat. And you want to find some sort of approximation with this training data, and you want this approximate function to be close to the target function. So you have this L, which is loss function, all right? And you have n piece of training data, n can be huge usually. And they try to find a minimum, global minimum or local minimum of this function, all right? Here I want to find global minimum. And in general, of course, f is non-convex. And we know non-convex optimization is NP hard problem. And as I mentioned earlier, the most popular method for machine learning still is this stochastic gradient descent method. However, we know this method needs to take gradient. Okay? And when you have bad functions, non-smooth functions, or sometimes you even don't have functions, because usually you only have data. You don't have even these functions. So therefore, the method that's gradient free seems to be a good alternative in those occasions. So that's kind of method we try to develop. Does not take gradient, only evaluate the function. Of course, we are not the first one to do this. I mean, this big industry, it's called meta heuristic methods. There are lots of them, which are actually learned from the nature, from insects, for example, birds and so on. And the earliest one is so-called simulated annealings and genetic algorithm. The one that I will focus on belongs to this class of the so-called swarming intelligence. So here you can see the swarming of n whatever, birds, fishes, whatever. And they interact in some way. It turns out all these insects or animals are very smart. Right? Individually, they do some kind of random motion, but they see what other people are doing. They try to follow. And the collective behavior seems to be very intelligent. So here we talk about AI stands for artificial intelligence. Here, my AI stands for animal intelligence. These animals actually are very, very smart. So for example, here you see, so there's some non-convex function. These particles are initially everywhere, and they tend to form some kind of consensus. They converge to one point. And that point, magically, is the global minimum. All right. So there are many works like this. Particle swarming and colony optimization, artificial bee colony optimization.
This one point is a fly trap.
Which one? This one?
This one point they converge to is a fly trap. So they're
But
not very intelligent.
if you go read this literature on so-called meta heuristic, this is what I stole from Wikipedia. This is what the people say on Wikipedia. So most literature on meta heuristics is experimental in nature, describing empirical results based on computer experiments. Many of the publications have been of poor quality. Flaws include the vagueness, lack of conceptual elaboration, poor experiment, ignorance of question. And here, what we want to develop actually interacting particle system, actually with rigorous mathematical theory. We prove convergence toward global minimum for general non-convex, high-dimensional functions. All right. So it want to be a little bit more than just heuristics. The starting point of our work is this two previous work. This group in Kaiserslautern and later Jose Carrillo in Imperial College joined the effort. What they do is they use this consensus type of model, particle models, which is very simple. It's a very simple model. So we have these m particles. The first one, forget about this heaviside function, it's not very important. So first one is a relaxation term. So this particle, this lambda is some positive number, it's a minus. Xj minus x bar star, and x bar star is some kind of average. Well, if you don't have this other term, basically from here, this ODE solution will converge exponentially fast toward this point. All right? So particle with, that's what the formation of consensus. They all converge to the same, it's a relaxation. Well, this is actually a Brownian motion term. Basically, if you only have that, you may get stuck into a local minimum, and this Brownian motion term, you look around the landscape, you try to get out with certain probability. You have this Brownian motion term. And the key, of course, is the choice of this consensus, I mean this average. So what they choose is there's some kind of a, here e to the minus beta L. L is the loss function, the function you want to minimize. And the minus beta is some constant. So this is basically a Gibbs distribution from statistical physics. And they can see if you, beta is like 1 over temperature, right, in Gibbs distribution. So if you choose beta to be very large, it's like low temperature, then you see that solution try to concentrate towards the smaller value of L. And then it is a weighted average. You put the xi here and then normalize it. All right. So what's nice about this particle system is that actually they can prove this consensus. All right. This that's the reason they use this model. You can prove if beta is sufficiently large and the particle system does form a consensus, and also this consensus is nothing but global equilibrium, and the convergence is exponentially fast. However, you need some conditions here. The lambda is drift rate, sigma is strength of the noise, and in their proof, they need 2 lambda bigger than d times sigma squared, where the d is the dimension of x. Okay. All right. So then mathematically, this is very nice. However, this d bothers us because d, if you do machine learning, and d can be, and the data can be millions. So that means that your drift rate. As you are already very close to global equilibrium, all of a sudden you are drift away. So this algorithm works very well for low dimensional problem, but fails terribly for high dimensional. And what we did actually, well, another point I want to emphasize is that the choice of this weighted average, the reason that it forms consensus is very easy to see. But why this consensus is the global minimum? That's because of this Laplace principle, which is a basic things from large deviation theory. All right. So if you take e to the minus beta L, integrate rho is the law of x, take a logarithm divided by beta, and this limit, beta going to infinity, is the minimum value of L. So that's called a Laplace principle, which is an important tool if you want to approximate an integral, for example, also from large deviation theory. So from here you see that's the choice. This choice of this Gibbs distribution allow you to get to this global minimum of this function. Right. What we did actually, we start from that model, we just did a very simple modification. Very simple one. The first term is exactly the same. We joined with Jose and Lei Li, again, I mentioned him earlier. Yuhua Zhu was my last PhD student from Wisconsin Medicine. She's now a postdoc at Stanford. So what we did actually, we did a very simple modification. If you look at this model here, what they have here, they use this isotropic Brownian motion. Basically, in every dimension, you use same amount of Brownian motion. What we did is we removed these 2 bars. We use this Brownian motion component-wise. And actually, the one we use is exactly geometric Brownian motion. This is a component-wise. It's exactly geometric Brownian motion. All right, so that's the only modification we do. And we do some other things. For example, you have this summation. This weighted average is a summation of many terms. We use this small random batch idea. Instead of sum of all terms, we choose each iteration, we choose a small number of random terms and add them, take average. We do those kind of things. All right. And now I just, with this one page, you understand why this is good. For example, if I assume this Heaviside function 1, doesn't matter. If I choose this average to be constant, so for this model, this SDE, if you choose this guy to be constant, you can solve this analytically. Then you can find, well, in our previous model, if you have these 2 bars, now this expect of x minus this average square time derivative is bounded by this 2 minus 2 lambda itself. That gives the exponential decay toward a. This Brownian motion term in the original model, you have the expected value x minus a squared for all dimensions, and you have add I from 1 to d. That's why this term gives you this d. And if you want this decay to a, you need this count to be negative. Therefore, 2 lambda is bigger than d sigma squared. But if you get rid of this bar, then essentially you get this term. Each direction you only have one component. You add them all, you give this one, there's no more d. So now from here you see that you only need 2 lambda bigger than sigma squared. So then this algorithm is dimension insensitive. It works for any dimension. To prove, then we have some theory, and at the beginning we could not prove it for the particle system. We take a mean field limit, we get PDEs, and for Planck equation we can prove theorems. So that's what we do. So if you, this is the continuous version, and go to infinity, the particle system become, again, this is drift diffusion now, this summation becomes this expected value of x times e to the Gibbs distribution. And this Brownian motion term, and this system corresponds to this Fock-Planck equation. This rho is the empirical measure, so this is drift term. X is drift toward this average. This is the Brownian motion term, which now becomes diffusion term. The mean field limit. And this average is this weighted average. So for this one, we assume that this loss function is strictly positive. This doesn't matter. If it's not strictly positive, you just add a constant to make it positive. You also assume essentially the second derivative is bounded. Well, the algorithm does not take derivative, but to prove theorem, we need to assume some regularity to prove the theorem. And then you check the variance of this x. And what we can prove, sorry, it's a little bit poor quality. Well, these are some conditions on the parameters. And the only thing you don't see is this parameter d, okay, dimension parameter is not here. So there's no d here. And then you can prove this, essentially the expected value of particle goes to the average, but this average is bounded by the global minimum plus all the 1 over beta. But beta is a large number. Beta, 1 over beta is temperature. So, I mean, what is a low temperature? Beta is 1 over temperature. This is like temperature. So basically, what you get is your 1 over beta distance from the global minimum. Okay. So for beta sufficient large, of course, you are in a small neighborhood of global minimum. And all these conditions are independent of dimension. And you can also do it for semi-discrete model. For example, for this particle mean field limit, if you for each time step you fix this average, so it does not depend on time, and then you can prove again under this very simple condition. Before we have a complicated condition of parameter, but it's a very simple clean condition. You can prove all these particles converge to some average, and this average is the global minimum. And convergence is exponential. More recently, actually, with Song Yi-ha in Seoul National University and his postdoc Dong-Hu Kim. Actually, we have theorem for the particle system, not for the mean field limit. We do not take the mean field limit. And basically, what we can prove is that particle I and j, when t goes to infinity, goes to 0. Distance between any two particles goes to 0. The probability that their distance bigger than epsilon, the probability t goes to infinity is 0 for any epsilon. So they all particles will converge to the same point. And the reason that before we have to do the mean field limit, and also Jose, these people, is because we're doing the L2 norm of the particle. If you do L2, actually, it's not the right norm. You get exponential growing because you use this ground wave inequality. And in the new work, actually, what we estimate is the diameter. It's really the longer distance between all these particles. It's diameter. Okay, take a maximum distance between particle I and particle j. And this is the right quantity to estimate. So that's what we did. And then essentially what we did is under these assumptions, basically 2 lambda because of sigma square, you show the particle xi and the particle xj will converge from the initial distance exponentially. E to the minus n is the iteration parameter. Yn actually has a limit which is positive. So you really do get exponential. They converge to each other exponentially fast. And the convergence, you also need some condition for the initial data, which basically means that you have n particles. Some particles need to be in the valley where the global minimum sits. Okay. So that's what this condition means. Then also, then we can show this limit is basically bounded by the global minimum plus over the 1 over beta. So now we do some numeric experiment. This is standard test case for machine learning, where this is for image processing. You have this, basically the image is represented by gray scales from 0 to 9. And we have the input data actually is a vector of dimension 700 something, which we will record the grayscale of each pixel. And here we consider single layer neural network. All right. So what we do is you have it's composition of a linear function with some this is called a rectified unit sphere, which is the rule x is x when x is positive and 0 otherwise. And this A is activation function. Here we choose the softmax, which looks like this: e to the xj divided by the summation of e to the xj. And the loss function is this entropy f y, sort of like algebra y times log fi. F is this with activation function. So this is a problem of 7,000 something. So it's optimization for it's non-local, it's non-convex, 7,000 problem. So we pick up, we use 100 particles. And what people do here is you use this training data to find this approximation function. Then you use a bunch of test data to see whether it works for test data. It's very much you show this machine 7,000 cats, and after a while you bring out a picture to let this machine to understand whether it's cats or something else. So we use the test data is 10,000 test data. So we get about, for all these different parameters, we get about 80% correct. And this machine learning, of course, you do not always get correct. The stochastic optimization does not guarantee every time you get the right solution, right? You make mistakes sometimes. And the question is what's the percentage of success? So for this very simple mining method, we get like 80%, about 80% success rate.
So your method is instead of the gradient, stochastic gradient descent.
No gradient. Yeah, it's not stochastic gradient. It's this random particle system.
Yeah. So you are replacing the normal
yes.
algorithm.
That's right.
Use,
Using by solving this very simple particle system with Brownian, geometric Brownian motion. And this problem is called a Rastrigan function. It's 20 dimension. It look crazy like this. A lot of local minimum, and this is global minimum. All right, 20-dimensional function. Well, the original algorithm by this Kaiser-Slautern group, it's a very low success rate because dimension is quite high, 20 dimension. On 50 particles, they get about 1/3 right. 200 particles is about 2/3 right. But we use the exact same parameters. We get from 50 particles about 200, it's about between 98 and 99%, even for a very complicated non-convex function. All right, so I conclude here. Of course, there are more works that need to be done. For example, analysis of conversion to global minimum for discrete systems. We have a proof of a consensus for discrete system, but we have not proved the convergence toward the global minimum. We have it for the continuous ODE, but not for the discrete version. And also, if you use random batch to replace the summation, and so far we do not have any proof for that. Also, it's also interesting to prove the mean field limit for these kind of systems. Then, of course, if you want to sell it to the machine learning community, you need more tests and error analysis in terms of different parameters. Because for this machine learning problem, finding the right parameter for specific point is very important. All right, so for that, I stop. Thank you very much.
Thank you. Questions?
So am I right if I say that you play with you replace the L2 norm by the
Diameter.
Yes. So the key is that the volume of a Euclidean ball goes to 0.
They go to 0, yes.
And the volume of an infinity norm.
That's right, yeah.
So I expect that you will have problem with the variance, no? So, I mean, if you push somewhere, then it blows up anywhere. So if you reduce sigma, which makes the algorithm converge, then probably the variance grows, no?
That's why you need the sigma. So in our theorem, actually, we did prove the variance go to 0.
The variance should depend on the dimension.
So where is
The variance, or the invariant. So does the invariant measure.
Remember, I defined the variance. The variance actually goes to 0, so this is a variance.
Okay.
So we did prove that the variance. I should have written that somewhere. Yeah, what we have is exactly the estimate on the variance. I should well there are several parts. I should have I forgot to put that part. We do have estimate on the variance
You do have.
under same conditions. The variance goes to 0. Even for I didn't put it here, but if you look at the earlier version with full Planck equation, we have the proof for the variance. Where v of t go to 0, v is the variance. Go to 0 exponentially fast.
Yes, but in this exponential, you have the dimension.
No. Here, these conditions does not have d there. It's a complicated. It's a complicated condition, but there's no d here. I'm sure you. D does not appear here. But later we have collinear condition. It's just this condition. It's again no d.
So you really.
You see this variance go to 0.
You completely get rid of the dimension.
Yeah, with the simple, you just use geometric Brownian motion instead of isotropic one.
Okay.
Further questions?
How does the number of particles enter in all your?
That's a very important question. The theorem works for any n, but if you have one particle, and as I said, the condition on the initial data, you need some particle to be in the value of this global minimum. If there's one particle somewhere, there's almost 0 probability it gets there. And if you one particle, if you try many times, then maybe 1 or 2 twice, it will be there. So you need a large number such that you essentially cover the value where you have this global minimum.
Okay.
So if even a large number, if you have no particle there, you'll fail. The stochastic optimization does not mean every time you get it converts there, but most time you will convert.
Further questions? I am fascinated by the difference between these two modes. One in which you are keeping the random division constant, and one in which you are changing it all the time.
Yeah.
Because, for example,
This is important, yes.
in opinion formation,
Yeah.
it somehow makes sense that when a rumor starts spreading, you want people maybe remain in small groups, but different groups.
Okay. Yes.
So
Actually, in the stochastic grid design method, people observe that they also have this transient Brownian motion. They actually reduce up the iteration progress, because when you're getting close, you don't want the Brownian motion. You don't want to swing too much. So one can, I mean, in principle, you can do similar things here, right? But those needs further studies.
Okay, if there are no further questions, thank you again.